Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 4 on combined shifting of functions. Now in the last couple of lessons we looked at both vertical shifting of functions and horizontal shifting of functions. And it's only natural to try to combine them both so that we can make more interesting and complex functions based on our parent functions. So let's get right into it and talk a little bit about vertical and horizontal shifting. And we want to, of course, review these two before we combine them. Now, in previous lessons, you learned how to individually move functions either vertically, up and down, or horizontally, left and right. And let's kind of review that a bit here, right? A vertical shift, you take an overall function and you add a constant to it. Now, it's going to be an upward shift if that constant's positive, and it's going to be a downward shift if that constant is negative. Of course, many times, instead of thinking about adding a constant, we think about, well, if we're adding a positive number, it's going to move the thing up, and if we subtract a positive number, it's going to move it down, right? Horizontal shifts, as we saw in our last lesson, work almost opposite of what you'd expect. This happens when we add or subtract a constant directly to the variable x before doing anything else in the function. We get a leftward shift if we end up adding a positive constant, and we get a rightward shift if we end up subtracting a positive constant or adding a negative constant, whichever way you want to think about it. But again, it's a little bit opposite of what you'd expect. You'd almost expect that if you added to x first, it would shift to the right, and if you subtracted from x first, it would shift to the left. But that's not the way it goes. So let's review this with our basic absolute value function in exercise number 1. Let's take a look. The function f of x equals absolute value of x is shown on the graph. Letter A. If g of x equals f of x minus 6, produce a formula for g of x and draw a graph of it on the grid. Label with its equation. All right. So this is actually a piece of cake to find its equation, right? Because all we want to do when we have a situation like this is we want to take whatever the formula is for f of x and replace f of x with that. So in other words, g of x is going to be the absolute value of x, because that is what f of x is equal to, minus 6. And of course that is going to be a downward shift by 6. So we're not going to create a table of values. In fact, the point here is to almost avoid that, to be able to say, all right, well, if I take my original absolute value function and I simply subtract 6 from it, I can now go over to this graph. I'm not going to do it with every nice point on this graph, but I can literally say, well, I've got 1, 2, 3, 4, 5, 6. I can move that turning point down 6 units. Maybe I'll take this point and move it down 6 units as well. And maybe this point and move it down 6 units just to kind of give me a little bit of a few extra points to work with. And then I draw in my graph, right? So this becomes g of x, a downward shift by 6 units. And again, it should make all the sense in the world given that the original y values were given by this expression, and then I just subtracted 6 units from each y value, not doing anything to the x's, and moved them down by 6 units. Now let's take a look at a horizontal shift in letter B. Letter B. If h of x equals f of x plus 3, produce a formula for h of x and draw a graph of it on the grid, label it with its equation. Now, this is a little bit more of a confusing notation, but the way you want to really look at it is, given the fact that f of x is equal to the absolute value of x, then f of x plus 3 will be the absolute value of x plus 3. So in this case, again, coming up with the formula, h of x will be the absolute value of x plus 3. Now remember, what this is because I'm adding directly to the x before I do anything else, it's now going to shift it horizontally. And because I'm adding 3 directly to the x, it's going to shift it to the left 3 units, right? So we're going to have a leftward shift by 3 units. And again, just like before, what I'm going to do is now I'm going to take my original graph and I'm simply going to take each point on it and shift it left 3 units. I don't need to do every single point, but it makes sense to take the turning point and shift it left 3 units. Maybe I'll take that point and shift it left 3 units and that point and shift it left 3 units. and we end up getting this graph. Let me just kind of go up a little bit, and that's going to be h of x. All right, so just a little bit of review on how both horizontal and vertical shifting works. Now let's move on and combine the two. Okay, so combining vertical and horizontal shifts. Vertical and horizontal shifts are independent of one another, right? It doesn't matter, right? If I shift it horizontally, the graph stays the same, it's just in a different location. And then I can shift it vertically, or I could shift it vertically and then horizontally. As long as I do the same kind of like amounts of shifts, then it should end up in the same place. So we can combine those two, and let's take a look at that in exercise number 2. The function f of x equals absolute value of x is shown graphed. Great. The function g of x is defined by g of x equals f of x plus 3 minus 6. Letter A, produce a formula for g of x. Well, think about it this way, right? This really is a combination of our last problem, right? G of x equals f of x plus 3 minus 6. Now, in the last problem, remember when we had h of x equals f of x plus 3, right? We just got h of x equals the absolute value of x plus 3. In this case, right, g of x being f of x plus 3, well, that will be absolute value of x plus 3, and then we need to subtract 6 from that result, right? So literally, I take my x plus 3, I substitute it in for x there, and then I subtract 6 from what I get. So there we have it, right? Now, you know, we probably understand already that this is going to combine both the horizontal and the vertical shift from the last one. But let's verify that by actually putting this into our calculator, creating a table of values, and then graphing that actual function on the grid. So for this, I'm going to have to bail out of here. Let me open up my calculator. The first thing I'd like to do is actually throw my absolute value function in, just so that we have that base function kind of sitting there. And then in f of x2, we'll throw in the other one. All right, now, if you can recall from a previous lesson, the absolute value on the TI Inspire is a little bit hard to find, but if you move just to the right of the 9 button, there's this sort of like jack of all trades button that's got all sorts of stuff in it. And one of those things all the way over on the left is the absolute value. So I'm going to just grab that. Now I do have to put in absolute value of x, and I'll just hit enter. There's our nice absolute value of x function. Okay, and now let me go into my menu, put in another function, and specifically I'll go back in here and I'll grab my absolute value, and that's now going to be the absolute value of x plus 3. I have to use my right arrow to get out of my absolute value bars. You want to make sure that you don't have both the x plus 3 and the minus 6 all inside of the absolute value bars, because then you'll just have x minus 3 in there, right, if the 3 plus negative 6 combine. All right, so now I'm going to hit enter. And we can already see that's what's happened to this graph is that we've moved it 3 units left and 6 units down. But we want to be able to create an accurate graph of that over here, and for that we need a table of values. So as always, to create our table of values, we're going to hit menu. We're going to go to option 7 for table, and we're going to put in a split screen table. All right, there's a lovely set of absolute values for f of x1. I need to hit right one, actually, enter. Okay, now I've got my f of x2 here, so this is going to be my table of values. Now there's a lot of values in this function, and what I probably should do is I should find its turning point, right? Oh, there's its turning point. Right? And just like a parabola, absolute values have turning points with symmetry. And I can see that, right? Because my y values go -3, -4, -5, -6, -5. And if I looked, it would be -4, -3, etc. So what I'm going to need to do now is take this table, write it down on my sheet, which means I got to go to the small view. Make sure you've got your table of values sitting there at this point. So I'm going to go into handheld only so that I can actually work and write at the same time. View full screen. Let me kind of just move it up a little bit here. I'll move this over here so I've got a little bit of room to create my XY table. I'm going to go with a horizontal table because that's what I have room for. And I think I'll just start it at that -6, -3, -5, -4, -4, -5, -3, -6. There's my turning point. -2, -5. I don't need to have every point I'm going to graph, but I need to have enough of them to sort of establish the pattern, which with absolute value is not too tricky. So I've got -1 and -4, 0, -3, and I think I'll just do one more, 1 and -2. All right, I'm going to put it back on this, and we'll minimize that, get it out of the way, and let's do some plotting now. I go to -6, -3, -5, -4, -4, -5. Starts to sound funny after a little while. There we go. -3, -6, -2, -5, -1, -4, 0, -3, and 1, -2. And that's going to be enough to kind of establish my pattern. So I do this, and label that g of x. Fantastic, right? So, and what I've seen definitively, right, is that easily I just combine the two shifts, right? The x plus 3 shifts my absolute value graph to the left 3. That -6 shifts it down 6 units. So suddenly my turning point, instead of being at 0, 0, is at -3, -6. Now, as a little final, just kind of review topic, letter C. What are the zeros of the function g of x? Remember, the zeros are simply another name for the x-intercepts, right? The locations where the function crosses the x-axis. Those happen to be right here and right here. Those are at x equals -9 and x equals 3. All right, that's it. So what's kind of nice is that really, in today's lesson, we really don't particularly have much that's new. Actually, let me just go back for a second. Yeah, okay, just making sure we hit everything in that exercise. We don't really have all that much that's new, because what we've got is we've got a vertical shift and a horizontal shift, right? We know exactly how they happen, okay? And so we just combine them together. Now, we want to be able to combine these vertical and horizontal shifts together in order to actually determine equations of functions based on shifts of parent functions. And we want to be able to do those with parent functions to produce original graphs. This will allow us to actually find equations of more complex functions. So let's take a look at exercise number 3. Two functions, f of x and g of x, are shown below. All right. Letter A, what is the formula for the function f of x? Test on your calculator if you're unsure. In other words, I want to know what the formula of this function is. Don't worry about g of x, only f of x. So you should know what the formula of that function is now. Pause the video and see if you can write it down. F of x equals what? Pause the video now. Well, hopefully you recognize this from a few lessons ago. This is simply the basic square root function. All right, so f of x equals the square root of x, the positive square root of x. Now, I can test that if I needed to in my calculator, but I can also just test it mentally, right? When I put 0 in for x, right, the square root of 0 is 0, so the point 0, 0 lies there. When I put 1 in for x, the square root of 1 is 1. So that makes sense. When I put 4 in for x, the square root of 4 is 2, so that's on there. When I put 9 in for x, the square root of 9 is 3, so that's in there. So it's the basic square root function, and we need to know what that looks like. Now, let's take a look at letter B. The function g of x can be defined by g of x equals f of x plus h plus k, where h and k are unknown constants. What are the values of h and k? Okay, fantastic. So now what we want to do is we want to look at g of x and we want to say, well, wait a second. G of x is just f of x that's been shifted in certain ways, and that will help tell us what the values of h and k are. So pause the video now and see if you can figure out what those are. All right, well, first let's talk about the shifts, right? G of x is f of x shifted 3 right and what? 6 up, right? 3 to the right and 6 up. Now remember, if we're shifting to the right, then whatever we're adding to the x has to be negative. So in this case, h is equal to -3, right? That 3 to the right tells us h is -3. But on the other hand, the fact that we shifted it up 6 units tells us that k must be equal to 6, right? Those have got to be the two. But the fact that we shifted right 3 means that we're subtracting 3 here or adding -3, whichever way. But in this problem, since they phrased it as f of x plus h has to be -3. And then the fact that we moved it up 6 units means that k has to be 6. We had to add 6 to the overall function. All right, but now we can actually write a formula for g of x based on both a and b. Pause the video now and see if you can write that formula. All right, well, since g of x equals f of x minus 3 plus 6, then we can say that g of x is the square root of x minus 3 plus 6. And we have just built, or can't come up with, the formula of a more complex function based on a more simple function. And finally, let's take a look at letter D. Use your calculator to verify the formula that you wrote is the correct one. Okay, and this is one of the beautiful things about our calculators, right? We can easily now take this function formula. Let me move this out of the way so we can see the plus 6. We can take this function formula, put it in our calculator, make sure maybe we have the correct window, and we can see that what we have is correct. And I think just like before, what I'd like to do is I'd like to put both of those formulas in there. I think just to make my life simple, I'm going to open up a new document and we'll put in a graph. Okay, so for f of x1, I'm just going to put in my basic square root of x graph. All right, that'll be good. And then for f of x2, remember for that, we had the square root of x minus 3. Again, I have to hit the right arrow to get out of that square root business. Oh, that's not what I wanted. Let's try this again. Square root of x minus 3, hit my right arrow, plus 6. Again, very, very important that you hit that right arrow so that that plus 6 is outside. Now, I can't see it because my window doesn't look like it does over here. My window over here is from -5 to 15 on my x-axis and from -5 to 10 on my y-axis. So just to make sure it looks exactly like it does on the paper, let's go in and set our window settings. I'm going to go from -5 to 15 in x, and I'm going to go from -5 to 10 in y, and now the two look pretty identical, right? And it's great because you really can kind of test to make sure that you've got the right formulas. It's a great use of technology. There's nothing wrong with it. And of course, you've got that technology, so you should use it. All right, let's get back into it. All right, now, often we will be asked or we will be shifting a function that is only represented by the graph. It's critical to properly identify what shifts are occurring. All right, so let's take a look at exercise 4. The function f of x is shown graphed below. The function g of x is defined by the relationship f of x minus 5 minus 3. How will the graph of g of x compare to that of f of x? All right, great. So I'd like you to pause the video now and try to answer based on the way that formula definition looks for g of x, how the graph of g of x will compare to this graph of f of x. Pause the video now and take a moment. All right, well, the first thing I always look for is, has anything been done directly to the x variable? Since we've subtracted 5 directly from the x variable, then what that means is we're shifting f of x 5 units to the right. F of x will get shifted 5 units right. And then I look sort of outside of those parentheses on f of x to see if I've added or subtracted anything. I have. I've subtracted 3. So that means it will and shifted 3 units down, right? So the x minus 5 is going to shift it 5 units to the right, and then the negative 3 is going to shift it 3 units down. Now, letter B, draw a graph of g of x on the grid. Well, that's simple, right? Anytime you have a situation like this, grab important points on the graph, shift them exactly the way you know the function has been shifted, and then reconnect them with curves or lines or whatever. So in this situation, whoops, what I'm going to do is I'm going to shift each one of these points 5 units right, 1, 2, 3, 4, 5, whoops, 5 and 3 units down, 1, 2, 3. So that's my first point, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3. Come on. And I really should connect these now with a straight edge ruler. But again, as usual, what I'm going to do is save some time and just do it freehand. All right. I do want to have them labeled, though. Okay. Primarily so that we can answer letter C. Let's take a look at letter C. State the domain and range of both f of x and g of x. All right, great. Remember, the domain are the inputs, the x values that exist on the function, and the range are all the y values that exist on the function. And I think I'm going to write both of these, or actually all 4 of these, using interval notation as opposed to set builder notation. So I'd like you to pause the video, and whether you write them with set builder or interval notation, see if you can answer these 2 questions. All right, for me, domain is always the easier one because literally I can look at f of x and I can say, f of x starts at an x value of -7 and it ends at an x value of +3. A little bit hard to tell, but ends at an x value of +3. So the domain of f of x goes from -7 to +3. Remember, I use those square brackets because, right, both of those endpoints are included. Let's also do the domain of g of x, right? The domain of g of x starts at x equals -2 and ends at x equals, I believe, 8. Yeah, at 8. Okay, so I can do -2 to 8. Now, as a side note, before we go on, whoops, there we go. That's easier. All right, before we actually move on and do the 2 ranges, I want to point something out, right? F of x was shifted 5 units right. And if you look at the 2 domains, right, if I take -7 and I shift it 5 units right, I'm at -2. If I take 3 and I shift it 5 units right, I'm at 8. So if I gave you the domain and I told you, right, of the original function, I gave you the domain, and I told you, this function's going to get shifted 5 units right, will be the new domain, you should be able to produce it by just adding 5 units to both of that. Now, the range is a little bit tougher, right, because for the range, I literally need to find the smallest value of y on the graph f of x, and that occurs here at y equals -4. I then need to find the largest value of y on f of x, and that occurs up here at y equals 8. So the range will be -4 up to 8. Same thing for the range of g of x, right? For the range of g of x, I look over here and I see, the lowest value on g of x is here at -7, and the highest value on g of x is +5. So -7, +5. And again, keep in mind, right, that we shifted f of x 3 units down, and all of a sudden, right, each one of these numbers got 3 units lower, right? -4 minus 3 is -7. 8 minus 3 is +5. So our entire range got shifted down by 3 units, which is exactly what you would expect it to be. You know, if we've got certain y values and then we shift them all up or down by a certain amount, then you should be able to take the minimum y value, the maximum y value, and either add or subtract to find the new ones. Okay. Now the final piece, and this is really an important one because it comes up quite a bit in these types of questions. Take a look at letter D. Give all solutions to the equation f of x equals g of x justify. All right, well, I've reproduced the graphs here so that we don't have to kind of keep going up and down. I'd like you to pause the video now and tell me what the solutions or solution is to this particular equation. All right, well, keep in mind, right, we can solve any equation graphically. Any equation we want, we can solve graphically by looking at the graph, finding any intersection of the two things, right? I've got f of x graphed here, I've got g of x graphed here, so I want to find their intersection points because that is literally where, right, these two things are equal. Now, all I want, though, is the x coordinate. So these two intersect at the point 0, 2, but the solution to this equation is x equals 0. And again, the idea is, right, when x is equal to 0, f of 0 is 2, and g of 0 is 2. So there's an x value where the f and g values are the same, where they're equal. And that's it, right? X equals 0. It's our only solution. Okay, let's wrap this up. One thing that I absolutely love about combined shifting of functions is that it works the way that you want it to. In other words, all you have to do is go back to your vertical and horizontal shifting. The vertical shifting happening when you add or subtract a number to the overall function. The horizontal shifting happening when you add or subtract directly to the x variable before doing anything else. And you can just identify them both individually and then say, well, here's my horizontal shift, here's my vertical shift. This allows us then to do a variety of things. It allows us to take a graph, if we know the shifts, produce a new graph, or it allows us to take a more complicated graph and come up with its equation if we can figure out what shifting has occurred to a simple parent function to produce that graph. All right, and we're going to see this time and time again in coming lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.